Now that we've talked a fair bit about forces, including using Gauss's law to find the fields, we want to talk about the energy associated with electric forces. All right, the good news is energy operates in electricity just as it does in mechanics. Specifically, the electric force turns out to be conservative, which is very, very useful. Remember that conservative forces are ones where the work done is independent of the path, and there exists a conservative energy whose 0 point is arbitrary, but whose change can be found as delta U is minus F ds from the path from A to B. It comes around, remember, delta U is, of course, the energy at B minus the energy at A. That's what delta means. But that difference is minus the work done going from A to B, and the work done from A to B is this integral of f dot ds, where ds is some path through space. All right, so ds is some arbitrary path through space from A to B, and we walk along it with, let's say, tangent, little steps ds, and we dot into that whatever the force is at that value. We do a dot product, and then we add them all up. This is a conceptual thing. We don't tend to do that much. We tend to use calculus, but that's the basic idea. Consider a parallel plate capacitor where, as we've seen, the electric field is constant. Let's call it E. Why not? Then the change in energy going from SI to SF, that is delta U, is minus the integral from SI to SF of F dot ds, but F is QE, and E is in the minus x hat direction, whereas the step is ds, and it's in the plus x hat direction. So their dot product is E ds with a minus sign because they're opposed. We can bring the minus sign outside, cancel the first minus sign. We can bring the E outside because it's constant field, and we get that the change in energy is QE times this integral. But this integral is almost trivial. The integral of ds is just S between SI and SF. But SF minus SI is just delta S, and so we get that delta U is QE delta S. Your textbook is unreasonably impressed with this, and the fact that it looks like, in some sense, a gravitational field, where we could write that delta U was some mass times something times a change in height. I guess we would say change in y. And so they're like, hey, look, we have the thing that creates the force. We have the field that carries the force, and we have something which is the distance we travel. And your textbook is really, really, really impressed by that. I don't know if it's as impressive as all that, but it's still kind of interesting that for this constant field, at least we get an energy that looks a little like MGH. So we can say a positive charge gains potential energy when moving against electric field lines. Energy is stored in the field. You can think of this as a positive charge swimming against a tide. It costs kinetic energy, which has to go somewhere, so it goes into the potential energy of the field. Conversely, a negative charge gains potential energy when moving with the field lines. The swimming analogy kind of breaks down that way. It doesn't really kind of make sense. All right, two positive charges are equal. Which one has more potential energy? And here we say that since A is closer to the positive thing, it would lose energy going from here to here. It would lose potential energy. Why? Because if I let A go, it would gain kinetic energy. It has to come from somewhere. So A must already have more, since it would have less by the time it reached B. Two negative charges are equal. Which one has more electric potential energy? Well, here, of course, B would gain energy going from this way, right? They would both flow towards the positive, and they would gain kinetic energy as they move towards the positive, giving it up from its kinetic energy, from its potential energy, and therefore it must be that B has more. Positive charge moves as shown. Its kinetic energy increases, remains constant, or decreases as it does that. And of course, it will be decreasing. And you can think of it a lot of different ways. There is a field which is coming out of the plate pointing that way. And you can think of this in a quasi-Newtonian fashion of, well, I've got a force pushing against me, so it's going to reduce my velocity, which reduces my kinetic energy. Or you can think that the field's going to do work on me, and it's negative work because it's opposed to the motion of moving, and that will take away kinetic energy. Or you can think that this positive charge is gaining energy as it's moving up against the positive charges, and so it must be losing kinetic energy to do that. All right, we can just run the simple integration here, the simple calculation. What are the electric energy between 2-point charges? In moving Q2, let's say we'll move Q2 out. And so the electric field going from X1 to X, we're moving, remember, Q2 from Xi to Xf. So we do our minus FDS work. The electric field, of course, is a point charge. This is the electric field now due to Q1. And we just do what is essentially some grungy algebra, and we find that the change in potential energy in moving from here to here is minus this product times 1 over times this thing to be evaluated. And then we have to do the actual grungy algebra, so we have a minus sign, we cancel that minus sign, 1 over xf minus 1 over xi. But we would expect this to be, since it's a delta, it's a final minus initial thing. And look, I've got a final minus initial thing. So it must be the potential energy between 2-point charges is 1 over 4 pi epsilon, the product of the charges over the distance separating them. Look, we arbitrarily chose the axis to be the line connecting the two. So it's more traditional to write this in terms of the distance by which they're separated. That is, the potential energy at some point is 1 over 4 pi epsilon naught, Q1 times Q2 over the distance between them. Notice the potential energy of the two-charge system, not of either charge. It makes no sense to say the potential energy of a single charge. Potential energy is a feature of systems. All right, it only exists because there are two charges between themselves. Hey, it's a 1 over r thing. It looks a little bit like gravitation did. All right, and even if they're moving, we could still use this as their energy between the two. They don't have to be fixed in place as long as this is the separation at a given moment. Also notice that this respects the signs of the charges. Two positive charges will possess a positive potential energy with respect to each other because they will tend to put away. Remember, systems will tend to accelerate towards lower potential energy. Two positive charges together should try to get further away, and this expression says if they got further away, their energy would be lower, which is what we'd expect. We would get the same thing for negative charges. They would want to repel as well, and if I move them further away, I would have a smaller potential energy, a smaller positive potential energy, which is a decrease. But a negative and a positive charge together possess a negative potential energy. Yeah, dun dun dun. But then remember, that doesn't really mean anything. But notice that if it's negative and we make r bigger, then we're making it a less negative number, right? And so we end up with the potential energy changing the way we'd want. They end up being attracted. Also, finally, keep in mind, we've implicitly chosen a 0 point for the energy. When two charges are infinitely far apart, they have no potential energy between them. We did that way back in the integral at some point. And ultimately, we did it basically by taking integration constant to be 0. And it makes sense. If two things are infinitely far apart, they're not interacting with each other, so it makes no sense to say they have some energy with respect to each other. But it's important to keep in mind that that was arbitrary, and we could change it if it ends up being useful. All right, a positive and negative charge are released from rest in vacuum. They move towards each other. As they do, what happens? A positive potential energy becomes more positive. A positive potential energy becomes less positive. A negative potential energy becomes more negative. A negative potential energy becomes less negative. A potential energy becomes a negative potential. A positive potential energy becomes a negative potential energy. All right. They spontaneously will do this, so we should be lowering their potential energy. So either it should be one of these two, either positive energy becoming less positive or a negative one becoming more negative. So it's lower. But we know that between the two, we have, since it's Q1 times Q2, that would be a negative number. So the actual winner is a negative number becoming more negative. Quick and dirty proof stolen from your textbook as to how we know electric forces are conservative. Any path away from Q1 can be approximated as circular arcs and radial lines, right? All the work done is along the radial line segments, which would be straight line, the equivalent to a straight line from I to F. Why not along curves? Because the field is radial. And if you go along a circular arc, then that's, of course, at right angles to a radius because it's along the tangent. So the dot product is 0. So only the radial segments contribute to any change in energy. But now we've turned it into a straight line segment from I to F. So the work done by the electric force can depend only on the initial and final position, but not the path taken to get there. All right, an interaction between two elementary particles causes an electron and a positron, that is a positive electron, to be shot out back to back with equal speeds. What minimum speed must each have when they are 100 femtometers apart in order to escape each other? Well, why don't they escape each other? Well, they're positive and negative, so they're going to attract each other in this. They get so far away that the force of attraction falls off. This is exactly analogous to gravitational escapes from surfaces that we talked about in Unit 6, I guess. So what we want to say is we have the energy at the start is the energy at the end. The energy at the start would be U plus K, and the energy at the end would, of course, be U final plus K final. If they're escaping, though, we want them to get infinitely far away, so that's 0. And we want them to have no kinetic energy. We want them to have just gotten to rest at the point that they reach infinity. So that leads to the weird thing that the total energy should be 0, which is a general thing for escape conditions. And over here, of course, we have that the energy is minus the electron charge of the electron and the electron charge of the positron. And I guess I'll put that as the electron, right? Over 4 pi epsilon naught over their initial separation plus 1/2 mv squared is 0. If you grind out the numbers, you find out that it's 5 times 10 to the 7 meters per second, which is crazy fast, right? That's like 1/15th the speed of light or something like that, because they were pretty close. Those are pretty close distance. They must be going really fast to escape the very strong attraction they feel at that very. Consider an electric dipole in a uniform electric field. A dipole, remember, is a positive and negative charge with some fixed separation between them. The charges being equal, but opposite in sign. And so in a uniform electric field, the positive charge is pulled along the field lines with the force QE, but the negative is pulled against the field lines with force QE, and those two things add to 0. So the dipole gets no net linear motion. On the other hand, the torque due to this force is clockwise, and the torque due to this force is clockwise, so the whole thing gets a clockwise torque. And we could figure it out by walking through and saying, well, delta U, which is minus FDS, is also minus integral of tau d theta, just a rotational equivalence, and between two angles as before. Be careful that we've used a common but kind of annoying symbol here. This P is not a momentum. It's the dipole moment. It's how big the dipole is. It's an unfortunate notation of which we have many. You've noticed electricity is scattered with them. All right, and so when we do some Granger calculus, or not so Granger calculus, and we find that the change in potential energy is minus P cosine theta between those two things. And again, it looks like we have a delta. So we can say that the potential energy of a dipole in an electric field, external electric field, is minus the dipole moment dotted into the electric field. It's minimized when the fields are aligned, and it's maximized when they're anti-aligned. And since in general systems tend towards the state of minimum potential energy, the dipole tends to align with the electric field, which is kind of nice to know. All right, so if we make an energy graph as a function of angle, we have a little bit more than one loop of the cosine here, one cycle, and we can see there will be some mechanical energy that it has based on, say, its initial potential energy when we first let it go, and it will, as before with energy graphs, bounce back and forth between these turning points, which are now going to be angles, and get stuck going back and forth like here. It's stable at this point, and it's unstable at 180, where it could be anti-aligned, and that's allowed but that's the case of maximal energy, and so if there's any deviation, it's going to swing around. Even though it's in equilibrium when it's anti-allowed, it's unstable that way.